This is some data from the Alaska Department of Public Health. On the right, it's showing the rate of overdose deaths per 10,000 people in the population. For Anchorage, as an example, there are 4.6 overdose deaths per 10,000 people who live in Anchorage. This would be an example of a cause-specific mortality rate because we're not looking at all of the people who died of any cause in Anchorage. This is just showing overdose deaths. The numerator is the people who overdosed from each geographic area, and the denominator is the population living in that area during the June 2022 to May 2023 time period. This shows the percentage of opioid-related overdose deaths by age and sex. In this case, the numerator is the cases of overdose death in that age range during that time period, and the denominator is all deaths from that cause during that time period. I wanted to show this example to point out that this is not a cause-specific mortality rate, because if you're looking at that pie chart, it is 100% of the deaths. A age-specific or cause-specific mortality rate would be a mortality rate that's limited to the particular age group, with the numerator as the number of deaths in that age group divided by the number of persons in that age group in the population. So again, does the denominator have everyone in the population in it? Or is the denominator only people with a certain condition or only people who died in a certain time frame? It's always good when you're looking at these graphs to try to figure out what was the numerator, what was the denominator, to better understand what you're actually looking at with the data. This slide shows deaths ranked by number of deaths per underlying cause of death. This is from the National Vital Statistics System, which recorded 3.2 million deaths in the United States from January to December of 2022. The authors of the report noted that overall death rates and COVID-19 associated death rates were highest among non-Hispanic Black or African American persons and non-Hispanic American Indian or Alaska Native persons. This data can guide public health policies and interventions for the populations experiencing higher mortality. Tying back to what we started talking about at the beginning of this class, when we see health disparities like that, it's helpful for epidemiologists and others working in public health to use that data to then try to figure out how can we design interventions to try to reduce these disparities. This chart is an example of counts because these are the actual number of deaths for each condition. So if you look on the x-axis, that's not a rate, it's actually showing you the number of deaths. Crude rates tell us the actual mortality, which is helpful because across different countries, most places are pretty good at recording deaths, but they're not as helpful for comparing two different populations as adjusted rates. Similar to the disparities in US data overall, Alaska data also demonstrates higher mortality rates among Alaska Native people compared to non-Native people in Alaska across all causes. On the x-axis this time, it's age-adjusted mortality rate per 100,000. And they have Alaska Native people in the lighter blue with Alaska non-Native people within the state in the darker blue. So if you go back to the socio-ecological model, think about some possible reasons for these differences. What would be some causes for cancer deaths among Alaska Native people to be so much higher compared to other people in the state? And the same with heart disease and injuries. This is the age-adjusted all-cause mortality rate per 100,000 of the population. So again, we have Alaska Native people statewide in the lighter blue and Alaska white people in the darker blue. And this is all causes combined together. You can see if you follow the darker blue line that all-cause mortality rate is decreasing more for white people in Alaska compared to the decrease for Alaska Native people statewide. So again, we're seeing a disparity in the data between white people in Alaska and Alaska Native people. I wanted to introduce the concept of survival analysis, but you don't need to know how to calculate Kaplan-Meier curves for this course. When I was in school, we learned how to do this by hand, but nowadays everyone does this with software. I just wanted you to be familiar with the concept and to know what this is if you see a graph like this on the left. The Kaplan-Meier method calculates the probability of survival at each time when an event occurs. So if someone in the study dies, you would calculate the probability of survival at that point. And that's a little different from the life table method, which you also might see in research papers. In that one, they calculate it at regular intervals. In this example, I put 1 through 10, but for Kaplan-Meier curves, you might have kind of weird points where you're actually recalculating the probability because it's based on when an event occurred. These aren't only used for death, even though it's called survival analysis. You can actually use it for any outcome when you're looking for a better understanding of how many people or things will make it from the first event to the second event. Classically, the first event would be diagnosis, and the end event might be cure or death, but it doesn't have to be. You could apply this same method to almost anything. These are helpful methods for comparing two interventions, like in this example, looking at a control treatment versus an experimental treatment, and you can visually assess the shape of the curves. But it's important to know that you have to compare the curves overall, and you have to use statistics to know if there is a statistically significant difference between the two. You can't directly compare 1 point on one with 1 point on the other because of how these were created. And you'll notice the little tick marks. Those are how people display when someone was lost to follow-up or disenrolled from the study. So that shows you that someone in the data set went missing at that point in time. There's some assumptions that are made when doing survival analysis like this that are important to be aware of. One of them is the assumption that anyone who dropped out of the study will have the same survival as the people who remained in the study. But this is often a questionable assumption. So if you're thinking about a long-term epidemiological study, if people drop out, it might be because of risk factors that might relate to the condition or the outcome. We'll talk about issues like that with studies more towards the end of the course. But while introducing this topic, I just wanted to go ahead and point that out, that there are some assumptions made with these methods that you have to kind of take it with a grain of salt. And it is useful for comparing two things, but it's mostly only helpful within that context. So it's good for estimating the effectiveness of a treatment or recovery rates or the probability of death over a specified time period, but you can't take data from a survival analysis or Kaplan-Meier curve and then use it like you might if this were a line graph of crude death rates, for example. It's not the same. Standardized mortality ratios are a way of expressing risk of dying from a particular cause. Both incidence of colon cancer and mortality from colon cancer is greater than twofold higher in Alaska Native people compared to the general U.S. white population. And the median age at diagnosis is 64 years for Alaska Native people, compared with 69 years for all U.S. races. So Alaska Native people are both getting colon cancer at higher rates and dying of colon cancer at higher rates, and also being diagnosed at younger ages compared to the general U.S. population. Colorectal cancer is the second leading cancer cause among Alaska Native people and accounts for 18% of cancers and 14% of cancer deaths. So this is a really significant area in need of more public health work in the state of Alaska. The difference in colorectal cancer incidence and mortality between Alaska Native people and the general U.S. population has persisted for more than 40 years. This is another example of a health disparity. Standardized mortality ratio is an indirect method of standardization. It allows for comparisons between groups, which is helpful in cases like this. You're going to divide the observed by the expected, and it can be expressed either as a percentage or as a ratio. If it's a ratio, if it's less than 1, then fewer deaths were observed than what would be expected. So maybe an intervention was protective and helped people survive. If it's the same, that means there was no difference. And if it's greater than 1, that means there were more deaths than expected. The under 5 mortality rate is a common way of measuring child survival and is often used when comparing different countries. It provides the probability a child will die before reaching the age of 5, expressed per 1,000 live births. To calculate it, you divide the deaths that occurred in those aged 0 days to less than 5 years by the live births during that time period. I pulled some data from the World Bank across different countries and different years to show changes over time and how different child survival is in different countries, even to the present day. If you look carefully at these numbers, see if anything looks like a pattern to you or if there's anything that surprises you. And one question for you to answer on your own is, why do you think the number was so high in Nigeria, specifically in 1990? Looking at information like this ties back to the socio-ecological model and thinking about all the things external to a person that impact public health. So far, we've defined epidemiology and its objectives, introduced ways of measuring disease in populations, and discussed how this differs from measuring health outcomes in individuals, provided a brief overview of social determinants of health and the socio-ecological model. We discussed measures of morbidity and mortality and looked at some data from Alaska and the United States. Next lecture will be about the distribution of disease in populations, including incidence and prevalence.